So we talk about stabilizers. Stabilizers nicely partition our Hilbert space into mutually orthogonal subspaces. One of them is the code subspace and the other are the error subspaces. Now the stabilizer, when restricted to the code space, they act as the identity. So every single vector in the code space is an eigenvector of every single stabilizer with the eigenvalue +1. Now the next class of operators I would like to consider are, well, we call them normalizers. So those are operators that respect the partition of the Hilbert space into those stabilizer subspaces, but they may act in a non-trivial way on the code subspace. So it's not like a stabilizer is the identity, but it turns out that the normalizers will act as operators that transform the encoded states here. One class of interesting operators of that kind, and we are going to restrict ourselves now to the Pauli group, are the operators which in the group theory language are called centralizers. So if you just consider all Pauli operators that commute with every single element of the stabilizer, but those operators are not in the stabilizer. So such a group of operators is called a centralizer of the stabilizer. So if you were to write it explicitly, so you say n is the centralizer if acting by conjugation on every single element from the stabilizer, you get the same element. So in this particular case, if I is equal to j, we are talking about stabilizer. There's a more general concept of a normalizer. Normalizer means that if you take a set of operators and those operators act by conjugation on every single element from the stabilizer, and the result of this operation is yet another element in the stabilizer, but not necessarily the same element, then we are talking about the normalizer of the stabilizer. Well, as it happens, when you just again confine yourself to the group of the Pauli operators, the two concepts are equivalent simply because you know that any two Pauli operators either commute or anti-commute. So if you look at this expression, you can see that n si and dagger is going to be equal to plus or minus si, right? Because I can just simply switch the order of those two operators, and if they commute, it's plus si, and if they don't, if they anti-commute, it's minus si. However, minus si is not possible here because we don't have -1 in our stabilizer. -1 doesn't stabilize anything, so so it has to be the case that we have plus si here. So in which particular case the normalizer is equal to the stabilizer. So that's just sort of a remark outside. So if you just want to have a specific example, then again let's consider the 3-qubit repetition code. And for example, if you take the code space which is spanned by 0, 0, 0 and 1, 1, 1 and consider the Pauli operator x tensor x tensor x. So if you just have 0, 0, 0 and under the action of x, 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 so it's a bit flip on every single qubit, you'll get 1, 1, 1. And then if you get on the other basis vector in this subspace, you get 0, 0, 0. So as you can see, this operator doesn't leave the code space, so that it maps vectors in the code space into vectors in the code space. And it has a nice logical meaning, right? So it just simply acts as a logical operator x on the encoded qubit. And we can also look at operators like z tensor z or minus y tensor y and identify them as logical operators. So on the encoded states they act as x or y or z operators. And there's more to that, you know, if you just look at x tensor x, it's not only this operator that will have the effect of the logical x. in fact, you can take this operator and multiply it by any element of the stabilizer, and you have the same result. So the stabilizer will, remember, stabilizer acts as the identity in this space, so will not affect the action of x, x, x. So in fact, if you then look at the class of operators, the normalizers, you can, the stabilizer is of course in the normalizer as well, so a trivial example. So you can nicely divide the whole normalizer into cosets which are generated by the stabilizer. So the stabilizer itself represents logical identity, but then if you take x, 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 and the whole class of operators x times any element of the stabilizer, you have logical x, and the same for logical y, and the same for logical z. So using that kind of operators, like x tensor x, or z tensor z, or y tensor y with a minus sign, we can implement logical operations x, y, z without leaving the code space. So once you're in the code space, you have those operations nicely within the code space. But if we do want to work within the code space, and we do, right? So we want to just perform all those operations within the code space without leaving code space. It's just we want only errors just to take us away from this code space. Then we need a larger set of operators. So not only the logical x, logical y, logical z, but we want to have a set of universal operations on quantum bits. So in general, we have to go outside the group, the Pauli group, and we want to look at the normalizer of the stabilizer in a larger group of all unitaries on n qubits. And of course, you know, the Pauli group is a subgroup here, and then you have a stabilizer as a subgroup of the Pauli and all those unitaries. So the normalizer that we are going to talk is not necessarily the normalizers within the Pauli's. Those give us logical x, logical y, logical z, but we also want to go outside to the more general unitary transformations. And here actually the Clifford group, remember Clifford? So it's a group that was generated by the Hadamard, the phase shift by with I, and the control not operation. So that group plays actually a nice role. So it turns out that many normalizers of the stabilizer, especially when you restrict yourself to the logical Clifford operations, can be constructed using some elements of the Clifford group. So it doesn't work for all the codes, but it's worth just perhaps to mention at this point that the normalizer of the stabilizer that come from the Clifford group are actually quite often used, and the Clifford actually operations are used to construct the encoding and the recovery in the stabilizer generated codes. So that is a few remarks about the normalizers, and then let's just talk a little bit about the general errors to conclude our discussion about the stabilizer codes.